Saturn is not what it looks like. From a telescope, even a small one, it appears gentle. A pale amber sphere wrapped in those iconic rings. It's the planet most people point to when asked which one they'd want to visit. Children draw it in science class. It hangs on bedroom ceilings as a plastic, glow-in-the-dark ornament. We have made it familiar, but everything we can actually see of Saturn, everything is a lie of perspective. The rings are not solid, the clouds are not peaceful. And the interior, the part we cannot see at all, is one of the strangest, most hostile, and most poorly understood environments in the entire solar system. No spacecraft has ever gone deep into Saturn, not one. And the more we learn, the clearer it becomes why. Before you can understand why going deep into Saturn is so dangerous, so genuinely problematic, you have to understand what Saturn actually is. Saturn is not a rocky planet. There is no surface, no place to land. If you descended through the outer atmosphere and kept going, you would not hit anything solid for a very long time. And by the time you did, you would no longer exist in any recognizable form. The planet is composed predominantly of hydrogen and helium. By volume, roughly 96% of Saturn's outer atmosphere is molecular hydrogen. The remaining 4% is almost entirely helium. Beyond those two elements, there are trace amounts of methane, ammonia, ethane, and other compounds. But hydrogen and helium are the story. Now, the outer atmosphere, the part we can actually see, is the cloud layer. And even that is divided into distinct regions. At the very top, where temperatures fall to around -130 degrees Celsius, you find the ammonia clouds. These are Saturn's highest visible features, the ones we photograph, the ones that form those famous pale bands. Roughly 170 kilometers below the cloud tops, the temperature climbs to around -70 degrees Celsius. Here, you find a second cloud deck, ammonium hydrosulfide. Clouds made of a chemical compound that, on Earth, we mainly associate with the smell of rotting eggs. Deeper still, around 130 kilometers below the tropopause, temperatures approach 0 degrees Celsius, and the clouds are made of water. Ordinary water ice, suspended in a planet that is almost entirely hydrogen. And the winds are extraordinary. Saturn is the second windiest place in the entire solar system. After Neptune, near the equator, wind speeds have been recorded at 1,800 kilometers per hour, 4 times faster than the most powerful hurricane ever measured on Earth. These are sustained, continuous winds, not gusts, not temporary storms. This is Saturn's baseline. Now consider what it would mean to try to fly something through that. In 1981, Voyager spacecraft captured something at Saturn's North Pole that scientists at first struggled to believe they were seeing correctly. A hexagon, not a circular storm. A hexagon, a 6-sided geometric shape, rotating and spanning a width more than twice the diameter of the entire Earth. Each side of the hexagon measures approximately 14,500 kilometers long. That single side is longer than the diameter of our entire planet. The full structure may be over 29,000 kilometers wide and roughly 300 kilometers deep. It rotates with a period of about 10 hours and 39 minutes, the same rotation rate as Saturn's interior radio emissions, which is thought to reflect the planet's true internal rotation. Saturn's hexagon was formally documented by scientist David Godfrey in 1987. When the Cassini mission arrived in 2004 and eventually observed the feature in visible light, it confirmed what the Voyager data had shown. The hexagon was still there rotating. Inside the hexagon sits a hurricane-like vortex, an eye with winds reaching over 550 kilometers per hour. The eye itself spans approximately 2,000 kilometers, 50 times larger than a typical hurricane eye on Earth. Here is what makes this genuinely strange. A hurricane on Earth typically lasts a week, maybe 2. The hexagon has been observed continuously for decades. It may have been present for centuries, No one knows. Multiple hypotheses exist for how such a shape forms. The leading explanation involves differential rotation, the way different layers of Saturn's atmosphere spin at different speeds, creating a boundary condition that forces the jet stream into a stable geometric pattern. Scientists have reproduced similar shapes in laboratory tanks of rotating fluid. Under the right conditions, you can get triangles, squares, pentagons, hexagons. The shape depends on the speed and density of the rotating layers, but reproducing it in a laboratory tank does not explain why it has remained stable for so long, or why it only appears at the North Pole and not the South. What we know so far is that the hexagon is a jet stream, a river of atmospheric gas moving at around 320 kilometers per hour, following a six-sided path around the pole. What we do not know is why it has maintained this configuration for as long as we have been able to observe it. And this is just the atmosphere. We have not yet gone any deeper. Below the cloud layers, below the storms, something begins to happen to hydrogen that has no equivalent anywhere in everyday human experience. As you descend into Saturn, pressure increases. The weight of all that atmosphere above begins to compress everything below. And hydrogen, the lightest element in the universe, responds to that pressure in a way that changes its very nature. In the outer layers, hydrogen is a gas. Normal molecular hydrogen, the same thing that makes up a large fraction of Earth's atmosphere and is used in fuel cells. But as pressure builds, the hydrogen begins to transition. It stops behaving like a gas and starts behaving like a liquid. There is no sharp line where this happens. The transition is gradual. The fog becomes thicker, the gas becomes denser, and at some point, you are no longer moving through a gas at all. You are moving through a liquid ocean of hydrogen, the largest ocean in the solar system. The temperature at this level is not cold. Despite being a gas giant far from the sun, Saturn is hot inside. This is because the immense pressure concentrates energy. Compress something hard enough and you heat it. Standard models suggest the core of Saturn reaches at least 11,700 degrees Celsius. That is hotter than the visible surface of the Sun. Saturn also radiates more energy into space than it receives from the Sun, about 2.5 times more. Something inside is generating heat. The most widely accepted hypothesis is that helium is slowly raining down through the liquid hydrogen. As heavier helium droplets fall through the lighter hydrogen, they release energy as heat through friction. Over billions of years, this process has generated enormous amounts of heat from within. Some researchers have proposed that diamonds may also rain down inside Saturn. Carbon, under sufficient pressure and temperature, can crystallize. The conditions inside Saturn's interior may allow carbon compounds from methane to transform into graphite and then into diamond crystals, which would fall deeper toward the core. This is a hypothesis. It has not been confirmed. But the physics, researchers argue, does not rule it out. Now we reach the layer that is most difficult to describe. Deeper still, where the pressure reaches millions of times the atmospheric pressure at Earth's surface, hydrogen undergoes a transformation that has no parallel in ordinary chemistry. It becomes metallic. This does not mean it turns solid, the way we think of steel or iron. It is still a liquid. But the extreme pressure forces electrons to break free from their parent hydrogen atoms. They flow through the liquid freely, the way electrons flow through copper wire when you flip a light switch. The liquid hydrogen becomes electrically conductive. This is metallic hydrogen. Scientists have known it must exist inside gas giants for decades, based on the mathematics of quantum mechanics and the observed behavior of materials under extreme pressure. Creating it in a laboratory has been extraordinarily difficult. Facilities like the National Ignition Facility have conducted experiments to compress hydrogen under controlled conditions, and the results have confirmed that the transition to metallic hydrogen is real, measurable, and occurs at pressures consistent with theoretical predictions. Here is why these matters for Saturn specifically. It is the metallic hydrogen layer that generates Saturn's magnetic field. Moving. Conducting liquid creates electrical currents, and electrical currents create magnetic fields. This is the same basic mechanism called a dynamo that generates Earth's magnetic field, though Earth's dynamo operates through molten iron rather than metallic hydrogen. Saturn's magnetic field is weaker than Jupiter's, about 1/20th the strength, but it is still substantial. Its magnetic moment is roughly 580 times that of Earth's, due to Saturn's much larger size. The field is also unusual in that it is almost perfectly symmetric, with Saturn's rotation axis, a characteristic that has puzzled researchers because most planetary dynamos produce fields with some tilt. The metallic hydrogen layer beneath Saturn's surface extends for tens of thousands of kilometers. It makes up the dominant interior volume of the planet, and no instrument we have ever built has been designed to survive it. At the center of all this, beneath the clouds, beneath the liquid hydrogen, beneath the ocean of metallic hydrogen, there is believed to be a core. But here is where scientists are most uncertain and most intrigued. Standard models suggest the core of Saturn should be a dense, rocky, metallic object. Similar in composition to Earth, iron, rock, silicate minerals, but under pressures and temperatures that are almost incomprehensible. Estimates place the core mass somewhere between 9 and 22 times the mass of Earth. Its diameter, based on modeling, would be around 25,000 kilometers. However, more recent data from Cassini's final orbits, the grand finale passes, in which the spacecraft flew directly through the gap between Saturn and its innermost rings, suggest something more complex. Measurements of Saturn's gravitational field, which can reveal how mass is distributed inside the planet, indicate that the core is not a sharply defined, compact object. Some research suggests the core may be diffuse, a fuzzy boundary between metallic hydrogen and the rocky material rather than a clean transition. The core might span as much as 60% of Saturn's total radius. Think of it not as a ball of rock inside a gas giant, but as a region where the planet gradually becomes more dense, more rocky, more metallic, without ever crossing a precise line. This is not what the simplest models predicted. What it means is that we do not know with precision what the center of Saturn looks like. We know it is hot. We know it is dense. We know it generates heat that radiates outward. But the exact structure, the exact composition, the nature of the transition between layers, these remain open questions. And we cannot simply go and look. In April 2017, after 13 years in orbit around Saturn, the Cassini spacecraft began its final chapter. The mission team called it the grand finale. Cassini was running low on fuel. The navigators had a choice: leave the spacecraft drifting uncontrolled, risking a future collision with one of Saturn's moons, or guide it deliberately into Saturn's atmosphere. They chose the atmosphere. There was a specific reason for this. By that point in the mission, Cassini data had revealed that two of Saturn's moons, Enceladus and Titan, might harbor conditions suitable for life. Enceladus was actively ejecting plumes of water vapor and organic material from a subsurface ocean. Titan had lakes of liquid methane and a dense nitrogen atmosphere with complex organic chemistry occurring within it. If Cassini were left uncontrolled and eventually crashed into either moon, it could carry terrestrial microorganisms, stowaways from Earth, surviving in dormant form on the spacecraft directly into a potentially habitable environment. To prevent this, NASA deliberately destroyed the spacecraft in Saturn's atmosphere. Between April and September 2017, Cassini completed 22 orbits that passed through the gap between Saturn and its innermost rings, a region no spacecraft had ever explored. Each pass brought the spacecraft closer, and the data it returned was unprecedented. Detailed measurements of Saturn's gravity and magnetic field, close-up imagery of the rings, direct sampling of the upper atmosphere. On the 15th of September 2017, Cassini entered Saturn's atmosphere for the last time. Its thrusters fired at full capacity to hold the antenna pointed toward Earth. For as long as it could maintain attitude control, it transmitted data back in real time, sending home readings of atmospheric composition, even as the increasing atmospheric density began to tear the spacecraft apart. Contact was lost at 4:55 in the morning Pacific time. The signal, traveling 83 minutes from Saturn to Earth, arrived as silence. Cassini burned up. It became part of the planet it had studied for over a decade. The mission ended. The data, however, continues to be analyzed today. So here is the question that the title of this film poses. Why hasn't NASA sent something into Saturn? Not a flyby. Something that actually goes deep. The answer is not a single thing. It is several things, layered one on top of another. The first problem is pressure. Saturn's atmosphere, even at relatively shallow depths, exerts pressure far beyond what any current spacecraft is designed to withstand. By the time you reach the metallic hydrogen layer, the pressure is millions of times greater than Earth's surface pressure. There is no material we currently manufacture that can survive that. The spacecraft would be crushed long before it reached anything of particular scientific interest. The second problem is heat. Saturn's core temperature exceeds 11,000 degrees Celsius. Even the outer layers of the planet are dramatically warmer than the cloud tops suggest. A probe descending through the atmosphere would face rapidly increasing temperatures that would destroy electronics, melt components, and eventually incinerate the entire structure. The third problem is transmission. For a probe to be scientifically useful, it must be able to send data back. At great depth inside Saturn, maintaining communication with Earth becomes increasingly difficult. The dense atmosphere absorbs radio signals. Once a probe has descended past a certain point, it may simply go silent. The fourth problem is the biological one. This may be the most philosophically interesting of all. Saturn itself is assigned what planetary protection protocols call a Category 2 designation, meaning there is no current scientific consensus that Saturn harbors conditions for life, but the designation still requires documentation and care. More significantly, Saturn's moons, particularly Enceladus and Titan, are considered potentially habitable environments. Any mission to the Saturn system must account for the risk of contaminating those moons with terrestrial biology, either accidentally during transit or from debris following a spacecraft's destruction. Cassini was intentionally destroyed to eliminate this risk. A future Saturn atmospheric probe would need to carry similar planetary protection considerations from the beginning. The fifth problem is simply that we do not know enough yet to know where to aim. The interior of Saturn is poorly mapped. We do not have a complete model of how its layers transition, where the metallic hydrogen begins, where the core ends. Without a precise target, a deep probe would be descending into conditions we cannot fully predict. There is a reason the destruction of Cassini was treated not as a failure, but as the correct scientific choice, and it has to do with a moon that, by rights, should not be as interesting as it is. Enceladus is small, only about 500 kilometers in diameter. It orbits Saturn at a distance that places it well within the planet's ring system. For most of the history of planetary science, it was considered a relatively unremarkable icy moon. In 2005, Cassini revealed that Enceladus is ejecting plumes of water vapor and icy particles from its southern polar region. Hundreds of geysers firing material into space from long parallel fissures in the ice, nicknamed the Tiger Stripes. The material being ejected includes water, carbon dioxide, methane, and more complex organic molecules. The plumes are the source of Saturn's E-ring. Cassini flew through those plumes twice. What it found suggested that the material was originating from a liquid water ocean beneath the ice, a subsurface sea kept liquid by tidal heating from Saturn's gravitational pull. Evidence of hydrothermal activity on the ocean floor was also found, the same kind of chemistry that sustains life in Earth's deep ocean vents. By 2011, NASA scientists were describing Enceladus as the most habitable spot beyond Earth in the solar system for life as we know it. This transformed the Saturn system from a place of purely geological interest into something more profound. Saturn's moons are not just moons. They are, potentially, inhabited worlds. And if they are inhabited, then every spacecraft we send to the Saturn system carries the responsibility of not introducing Earth biology into that system. A careless mission could contaminate the very thing we are trying to find. Future mission concepts, including a proposed lander for Enceladus, developed by scientists at ESA, are being designed from the ground up with strict planetary protection requirements. Bioshields. Disposal plans that ensure a spacecraft cannot survive long enough to accidentally collide with a moon of interest. We are learning, slowly, that exploring Saturn's system is not just an engineering challenge, it is an ethical one. And then there is Titan. Saturn's largest moon is bigger than the planet Mercury. It is the only moon in the solar system with a dense, substantial atmosphere, nitrogen-based, with methane playing the role that water plays on Earth. There are clouds of methane, rain of methane, rivers and lakes and seas of liquid methane on the surface, including a body of liquid almost the size of the Caspian Sea. Beneath Titan's surface, gravity measurements from Cassini suggest the existence of a liquid water ocean, buried under roughly 100 kilometers of ice. Titan's interior may be warm enough and chemically rich enough to sustain conditions worth studying closely. In 2019, NASA selected a mission called Dragonfly, a rotorcraft lander, essentially an octocopter designed to fly through Titan's thick atmosphere and land at multiple sites across the surface. Dragonfly is scheduled to launch in July 2028, with arrival at Titan anticipated in 2034. Titan's atmosphere is 4 times denser than Earth's, and its gravity is only about 14% of Earth's. These conditions make flight easier, not harder. Dragonfly will be able to cover more than 170 kilometers during its mission, hopping between scientifically interesting sites, dune fields, an impact crater called Selk, regions where liquid water may have interacted with organic compounds on the surface. The mission is specifically designed to investigate prebiotic chemistry, the chemistry that precedes biology. Not to find life directly, but to understand how far toward life the chemistry on Titan has progressed. It is one of the most ambitious planetary science missions ever proposed, and it goes to a moon of Saturn, not Saturn itself. That distinction is deliberate. Saturn has been studied by human eyes for thousands of years. We have named it after a god. We have built mythology around it. We sent 4 spacecraft to its system. One of them stayed for 13 years and returned data that is still being analyzed today. And yet, we do not know precisely how fast Saturn rotates. Different measurement systems yield different answers, and reconciling them requires understanding the interior in ways we currently cannot. We do not know the exact structure of its core. We do not know with certainty why the hexagon exists or how long it has persisted. We do not fully understand the mechanism that generates its excess internal heat. We do not know the age of its rings, with confidence estimates range from about 100 million years to over 4 billion years, a difference that matters enormously for understanding how the Saturn system formed. We have never sent anything into Saturn's deep atmosphere. We have never sampled the layers below the clouds. We have never directly measured the conditions in the metallic hydrogen region. We have inferred, modeled, and calculated, but we have not looked. The reasons are real. The pressure would destroy any instrument we could currently build. The heat would incinerate it. The distance makes communication difficult. The planetary protection concerns are genuine and serious. But here is what the data suggests. Saturn's interior is not simply a scaled version of what we already understand. It is a different regime of matter entirely. Hydrogen that conducts electricity, possibly diamond rain, a core that may be diffuse rather than solid, a magnetic field generated by mechanisms we can only partially model. Some researchers believe that a better understanding of Saturn's interior would fundamentally revise our models of how gas giants form. And since gas giants are among the most common types of planets discovered around other stars, that revision would have implications for how we understand planetary systems across the galaxy. So when you look at Saturn in a telescope, pale and ringed and oddly peaceful against the dark, try to hold two things at once. There is the Saturn you can see, the one that has inspired wonder for thousands of years, the one that makes children point upward on clear nights. And then there is the Saturn beneath the surface, the one we cannot reach, the one where hydrogen becomes metal, where pressure eliminates any distinction between solid and liquid, where temperatures exceed the surface of the sun, and where the most fundamental questions about how planets are built remain unanswered. For now, all we can do is watch and build better instruments, and eventually send something that can survive a little longer, descend a little deeper, and send back a little more data before going silent. We are not scared of Saturn, not exactly. We are humbled by it.